Namaste everyone, welcome to the second PUC physics class. We were in magnetism and matter. So now in the magnetism and matter we will study about terrestrial magnetism. Earth's magnetism. How does Earth behave like a magnet? Right? Namaste, welcome to the class. How do we measure the Earth's magnetic field? Earth behaves like a magnet. It has its own magnetic field. And what is the reason for Earth's magnetic field? Of course, so many researches are going on to find out the reason for the Earth's magnetic field. So far, we feel that Earth's magnetic field may be because of the motion of the molten metal that is, which is in the molten form. That metal is in the molten form inside the Earth crust. That motion gives the magnetic field. That may be the reason. But whatever it is, Earth behaves like as if there is a magnet inside. There is no magnet inside. The whole Earth itself is acting like a magnet, remember. There is no separate magnet inside the Earth. But we can feel that because of the Earth's magnetic field like this, right? Like this. Because of the Earth's magnetic field like this. So, this has become a little smaller. So because of this magnetic field, it's not symmetrical. Yeah, like this and like this and like this. We can feel that there is a magnet like this inside the Earth. As if there is a magnet inside the Earth like this, Earth behaves or gives the magnetic field lines. So there are magnetic field lines around the Earth. So this is the north pole of the Earth, this is the south pole of the Earth. So Earth behaves like a magnet, but there is no magnet like this, so better I remove it. And the magnetic field lines cross the Earth at every point. Now, how do we measure the strength of the Earth's magnetic field at different points? If you go to the North Pole, if you go to the equator, if you go to the South Pole, how will be the magnetic field lines? And that depends on the place. Earth's magnetic field varies from place to place, and its direction varies from place to place. Whether Earth's magnetic field is vertical to the Earth or parallel to the Earth, and we can measure it using a magnetic needle, whether Earth's magnetic field is parallel to the Earth or whether it is perpendicular to the Earth or whether it makes an angle with the Earth. Suppose you have a magnetic needle like this. You know that the magnetic field, if it is placed on the table, magnetic field starts from north and ends in south outside, but inside it moves from south to north, so like this. Now we place a small magnetic needle here. The magnetic needle stands like this, correct? It stands north here, south here, like this. If it is placed here, it will stand somewhat right. It will stand with this north here and south here, like this. So it will stand like this. That is the magnetic field lines. Magnetic field lines are the directions along which a small magnetic needle will stand. And by keeping the magnetic needle, of course, right. By keeping the magnetic needle like this, we draw the magnetic field lines around the Earth. Okay. Now, so Earth has its own magnetic field. Now we will take a magnetic needle. And you know that you have done the experiment, and your teacher in the lower classes must have told that any magnet which is suspended freely, if I take a magnet like this, do I have full chalk? Yes, it is here. If I have a magnetic needle which is suspended like this, it will stand in the north-south direction. Imagine that this is the north-south, or this is the north-south, say. If it stands in the north-south direction, say this is north, this is south. And if you are looking at the north, and then towards your right you will have east, this is west. So north, south, east, west, you will have it like this. Now if a magnetic needle is made to rotate like this, and if it stands like this, does it mean that Earth's magnetic field is like this? You can't come to the conclusion immediately. Why, sir? A magnetic needle suspended like this or made to rotate with an axis like this, it comes to rest like this. Whether it is coming to rest in the direction of magnetic field? No, because this magnetic needle is not free to rotate in this direction. It is free to rotate only in this direction, only in one plane. It is not free to rotate anywhere else. Earth's magnetic field need not be like this way only. It may be like this way also. It may be directed like this. if the Earth's magnetic field is like this, and if you try to find out this Earth's magnetic field which is aligned to the Earth, hope you are following my explanation. If this is the surface of the Earth, if the magnetic field of the Earth is not parallel to the Earth, suppose it is like this, say, at a place, at some place, you get a magnetic field like this at some place? Yeah, you get it here, right? You see, it is starting from here like this, ending it like this. It is neither parallel to the Earth nor vertical to the Earth. Here also, it is neither parallel nor vertical. Whereas here it is vertical. Here it is vertical, vertically inside. Here vertically going out. But here it is not vertical. And at such a place, if you place a needle, magnetic compass, with this needle turning in this plane, how can it stand like this? Because that needle has no freedom to vibrate like this. It has no freedom to vibrate like this. It has freedom to turn only like this. I will show you a compass. See, in this compass, yeah, right. In this compass, there is a needle. Can you see? I can show it very close to the this camera. Can you see a needle here? So here is a black needle. Can you see that? That black needle, black one, this one. This black one is the magnetic needle. And there is a point red marked. Can you see that red marked point? And that red mark, can you see it here? Where is that red mark? Yeah, it is here on the upper side, right? On the upper side you have a red mark, and that red mark is the North Pole. But now this needle has the freedom to rotate only in this plane. It can rotate in this plane, correct? It can rotate only in this plane, and it has no freedom to rotate like this. Because this needle, how can instead of turning like this, how can it turn like this? Not possible, right? And the same thing happens. If you want to find out the Earth's magnetic field, you have to keep the needle like this. So any needle, okay, any needle placed, see, I will show the needle in terms of this chalk. I'll show the needle in the form of chalk. I think you can see this chalk. Yes. I'll place it like this. This is the needle inside it, but because I can't show it like this. If you place a needle which is free to rotate like this is free to rotate like this, only like this. It is not free to rotate like this, correct? A suspended magnet. Here I have to bring you some imagination, that is more in this class. A suspended magnet, suspended means you have to tie it with a thread here in the middle. It can rotate like this, correct? With this axis. But can it rotate like this? No. That means if Earth's magnetic field is like this, and we are trying to get that Earth's magnetic field with a needle like this, which is free to rotate like this, how can you find out this magnetic field with a needle turning like this? Not possible, isn't it? Hope you have followed. So if the Earth's magnetic field is like this magnetic needle which is turning like this cannot show that Earth's magnetic field which is like this, because it has no freedom to turn like this. Then if you want to find out the actual Earth's magnetic field, then what you have to do is, you have to pivot a needle, you have to suspend a needle in such a way that it can rotate in any plane, like this, like this, like this, like this, any plane. So how to have such a needle? You have to have a hole here and a lever there, and it can rotate in any plane, like this, like this. Then it will stand like this. Then you can say that the Earth's magnetic field is like this. It is neither vertical nor horizontal, and it is making an angle. Then you can say that. But using this compass, you can purchase such a compass, and you can have a very small compass. So small compass is available in a shop, and if it is made to turn like this, how can this magnetic field, or how can this needle show this magnetic field? It cannot show. It can show only this direction. So a freely suspended magnet from the center stands always in the north-south direction, like this. That means partly you are in the direction of magnetic field. You may not be like this, but you are coming towards very close to the direction of magnetic field. Now this is the direction along which it turns. Now once you get a part direction, magnetic field should be in this direction somewhere, but it may be like this way also, like this way also, like this way also, we don't know. Because this needle which is free to rotate like this has come like this, but it is not free to rotate like this. Now turn this compass like this here. Understood? Because this compass which contains magnetic needle which can turn like this is showing the magnetic field like this, but actual magnetic needle is like this. So what I can do, I can turn this compass like this so that I give freedom for the needle to turn like this. You produce such a compass. So now come to the first point. Any freely suspended magnet stands in the north-south direction. Now in this north-south direction, you see, freely suspended magnet has a axis which is vertical to the earth and its plane of rotation parallel to the earth. Please hear my words very carefully. A freely suspended magnet has its axis vertical to the earth, plane of rotation parallel to the earth, right? Horizontal, plane of rotation. Now turn it, that means invert it. This compass is taken and kept like this, because you know that partly it is in the north-south. Okay? Make it to turn like this. That means its axis horizontal to the earth, plane vertical to the earth. Have you followed this? This needle has its axis of turning vertical to the earth and plane parallel to the earth. Now this needle has its plane of rotation vertical to the earth and axis parallel to that. Produce such a needle, and it is here. That is called dip machine, right? Or this is how a magnetic, see here, you can see a needle turning like this. So see the difference between this compass and this compass. This is dip needle, this one. This is just compass needle, which will help us to show north-south, that's all. It doesn't help us to show exact magnetic field direction, because it is running parallel to the earth. It is rotating like this in a plane parallel to the earth. It is not rotating like this. Now you produce a dip needle like this. See, this is dip needle. I'll show you, right? Can you see a magnet suspended? Now where is the axis of this magnet, right? I can show you so that there is no reflection. Yeah, right. This is the dip needle. Can you see this? Now here you can see a needle which is turning, right? This is the needle, vertical, and this is the rod to which its plane is, axis is fixed. Axis is like this, isn't it? Axis is like this, and the needle is turning and it is standing. See how does the needle stand here? Can you see the needle standing? Is it vertical to the earth? Is it horizontal to the earth? It is neither making vertical and nor making horizontal. It can turn in different angles, okay? It can turn, and even the whole this instrument can be turned. Okay, you see, it is making an angle with the surface of the earth. That means Earth's magnetic field is neither parallel nor horizontal. It is something like this. So this is the dip machine, right? You can see a needle, and this is horizontal, and this is the axis of rotation. Axis of rotation, which is parallel to the surface of the earth, and plane of rotation like this is vertical to the earth. Okay, I will keep it here and I will bring it back again. Right. Now, so you should have a needle not rotating like this. You should have a needle rotating like this. A needle rotating like this in this plane will stand like this. This is the dip machine. Okay. You should have a needle which is rotating like this. It makes an angle like this. So this is the needle, okay? That shows this is the surface of the earth. Earth's magnetic field is neither horizontal nor vertical. That is at this place. It may be vertical here. It may be horizontal. Yeah, here you see, if you go to the equator, magnetic field is exactly horizontal. It is like this. Here it is horizontal. Of course, if I can change this magnetic field lines like this, it is parallel. Here it is parallel to the earth. Here it is vertical to the earth. Here it is vertical to the earth. Here it is neither parallel nor vertical. Now, if you take such a needle which can rotate in a plane which is vertical to the earth and with its axis parallel to the earth, if you take such a needle, how much angle does it make with the surface of the earth? That is called angle of dip or inclination. Angle of dip or inclination. So here you have so many things to define. What is dip or inclination? Dip is the angle made by a needle, magnetic needle, free to rotate in a vertical plane, and angle made by that needle with the surface of the earth. Angle made by a needle which is free to rotate in the vertical plane with the surface of the earth is called angle of dip or inclination. Now, did you follow that definition? Angle made by a needle. I didn't bring the pen here today, so otherwise I would have hold the pen. Or I have a very large scale, right? Say this is a magnetic needle. This is very beautiful. This is a magnetic needle. If the needle is turning like this, then this is a needle which is turning parallel to the surface of the earth, but its axis is vertical. Now take a needle which can turn like this. A needle which can turn like this is turning in a plane which is vertical to the earth, and axis is parallel to the earth. So a magnetic needle turning in a plane vertical to the earth makes an angle with the surface of the earth. So angle made by a magnetic needle which is free to rotate in a plane vertical to the earth and with the surface of the earth, that angle is called angle of inclination. Now question is, what are the values of angle of inclination? Angle of dip. Angle of dip. You will get a definition, different definition for angle of dip also later. Dip may vary from 0 to 90, isn't it? It may be 30, 40, 60, many angles. What is the angle of dip at the poles? Angle of dip at the poles is 90 degrees. So, imagine you are standing at the poles. Where you are standing now? You are standing at the poles. You are standing here. If you are standing here, you will be standing like this. If you are standing at the south pole, you will be standing like this. At the equator, you will be standing like this. You know this, right? Earth attracts every object towards its center. Once you go to the space, there is nothing like upside and upwards and downwards, nothing like that. Space is open everywhere. So don't compare this with respect to the surface of the earth. This is independent earth now. So this is the axis. And here, if you look above, then the magnetic field lines are coming out of the north pole like this. Like this. Here, they are going into the south pole like this. Right? They are vertical. Now if you take the dip needle, I'll bring it back. If you take the dip needle to the north pole and keep it here, at this place, if you take the dip needle and keep it here, how does the needle stand? Won't it stand vertical? Because this needle has the freedom to align itself in the direction of any magnetic field. The magnetic field is vertical like this. So dip needle stands vertical if it is kept on the top of the earth surface. I can show it like this. I have brought so many things today in the class. See, this is earth. Okay, this is earth. And you know, yes, this is the north pole of the earth. How will be the magnetic lines in this north pole? They will be somehow some circles I have to do. Yeah, the magnetic field lines are coming from here and going like this. They are vertically like this. So if you place this needle here, magnetic field line will be coming like this. How does this needle stand? Vertical, right? So at the top of the earth, of course, I'll be bringing this again and again. At the top of the earth's surface, this dip needle should make like this, an angle like this, like this. So theta is 90. It stands vertical to the earth. So angle made by the dip needle at the top of the earth, that is the north pole of the earth, is 90. So dip is 90 at the poles and 0 at the equator. Why 0 at the equator? Suppose you are standing here. How are the magnetic field lines passing? They are parallel to the earth. They are parallel to the earth here. That means the dip needle should stand. Suppose you keep a dip needle here. It should stand parallel to the earth. Here it should stand vertical to the earth. Here it should stand like this. Here it should stand like this. So angle of dip or inclination is 0 at the equator. What do you mean by 0 at the equator? That needle should stand like this at the equator because all the magnetic field lines are passing parallel to the surface of the earth at the equator. So they are traveling like this at the equator, right? So at the poles dip is 90, at the equator it is 0. Somewhere here, you see, somewhere here, neither parallel nor horizontal. Dip angle may be 40 degrees, 60 degrees, 55 degrees. So it varies from place to place. Now, We will come back to that needle which is rotating in this plane. You come back to that needle which is turning like this. Any magnetic needle which is free to rotate in a horizontal plane stands in the north-south direction. It always stands in the north-south direction. So whether you place that needle here or here or here, anywhere, it shows the north pole shows the north direction like this. Okay, now if this shows the direction like this, you build a wall which is passing through this chalk piece. Magnetic needle, it's not the chalk piece. You build a wall passing through the magnetic needle and vertical to the earth. That is called magnetic meridian. Now my question is, this shows north pole, right? North, right? Any freely suspended magnet which is free to rotate in the plane which is parallel to the earth, not like this. This is a plane which is perpendicular to the earth. This is rotating in a plane which is parallel to the earth. Will stand in the north-south direction. I have already told north, south, east, west. So if it stands like this, you build a wall like this, passing through a freely suspended magnet, axis of the freely suspended magnet. A plane passing through the freely suspended magnet and vertical to the earth. Go on building it. Will you reach the earth's north pole? No. Because that plane is called magnetic meridian. So define magnetic meridian. Magnetic meridian is a plane passing through magnetic meridian is a plane, vertical to the earth, vertical plane passing through the axis of a freely suspended magnet. If Earth's geographic north is here and geographic south is here, then Earth's magnetic field, if Earth's geographic north and souths are here, then Earth's magnetic field is tilted like this. It is not exactly towards geographic north and geographic south. So if you suspend a magnet on the surface of the earth, it will stand like this, not like this. It doesn't stand parallel to this, it will stand parallel to the Earth's magnetic field. So if you go on building a wall like this, you will reach here, right? You will reach here. And this is called magnetic meridian, and this is magnetic north and this is magnetic south. This is geographic north and geographic south. See, now we are going to have some interesting features. So if a freely suspended magnet stands like this, right, like this shows north, this shows south, east, west. If you build a wall like this, what do you call magnetic meridian? A plane passing vertical to the earth and through the axis of a freely suspended magnet. If you go on building it, you will reach a point which is by the side of the geographic north, not exactly at the geographic north, because magnetic north is not exactly like the geographic north. That plane passing through the axis of a freely suspended magnet and vertical to the earth is called magnetic meridian. Now you tell me that dip needle should be rotating in the magnetic meridian, isn't it? Its plane should be magnetic meridian. Then it will show the actual Earth's magnetic field. I have drawn a diagram here, right? This was the Earth's surface. This was the Earth's surface, and the Earth's magnetic field was like this. It was making some angle. So if you take the dip needle and keep it here. Suppose you take a compass will show only this direction because it cannot rotate like this. It can rotate only like this. So it shows only this direction. But this dip needle will show like this because it can rotate like this. That's why it can show exact Earth's magnetic field. Whereas this compass needle can show only this much. It cannot show this one. It can show only this much. But a needle which is free to rotate like this can show this one. Okay, now that means, can I say that needle in the dip machine, it is rotating in the magnetic meridian, right? This is magnetic meridian. A plane which is vertical to the earth and passing through the axis of a freely suspended magnet. Now, if you take the earth like this is geographic north and geographic south. This is geographic north and this is geographic south. The magnetic north and south may be at different places. It may be like this. Magnetic north and south, they are different. Now this is geographic north and geographic south. Okay. Now, you pass an axis or take a knife and cut this cake from geographic north to geographic south like this, right? Cut it like this. Then that plane is called geographic meridian. A vertical plane passing through the geographic north and south. This is geographic north and this is geographic south. A vertical plane, a plane which is passing vertical to the earth, but it should contain geographic north and south. That is called a geographic meridian. So you have two meridians. Meridian means plane actually here. What is geographic meridian? A vertical plane passing through the geographic north and south poles of the earth. If you take an apple, cut it from the top and bottom of the apple like this, exactly like this. You will get a plane. A plane passing through the geographic north and south poles of the earth, but vertical to the earth. That is called geographic meridian. And a vertical plane passing through the freely suspended magnet axis is called magnetic meridian. Now, geographic meridian and magnetic meridian are not aligned exactly at a same plane. They are making some angle. Angle between geographic meridian and magnetic meridian is called angle of declination, delta. This is magnetic meridian, this is geographic meridian, and this is called angle of declination or delta. You have so many definitions and so many things to remember. All of a sudden you can't understand it. You have to go on thinking about it. Then only you can understand. So what is declination? Declination is the angle between geographic meridian and magnetic meridian. What is magnetic meridian? A vertical plane to the earth. That means if you take an apple and cut it using a knife, similarly you have to cut the earth. But that knife should pass through geographic north and south poles. So you have to cut it like this. A vertical plane passing through the geographic and north and south poles of the earth. That is called geographic meridian. A vertical plane passing through the freely suspended magnet. Freely suspended magnet stands in the north-south direction. That's why we take it. A vertical plane passing through the freely suspended magnet, axis of the freely suspended magnet. That is called magnetic meridian. And geographic meridian and magnetic meridians make an angle with each other. Angle between geographic and magnetic meridian is called angle of declination. So if a freely suspended magnet stands like this, if you build a wall like this, that is called magnetic meridian. Keep on building it. You don't reach geographic north. You will reach magnetic north. Right? And if you exactly see the north and south poles of the earth and keep on building a wall, then you will reach here. That is they make an angle. Now, very interesting factor is whether, my question is, what about declination? Whether declination is the same everywhere. That is very interesting. The angle between geographic meridian and magnetic meridian, whether it makes the same angle everywhere. Whether declination is same everywhere. However, we have understood inclination is not same everywhere. Inclination is the angle made by the magnetic needle, which is free to rotate in a vertical plane. So it doesn't make the same angle everywhere. That is very true. We know it because it makes an angle 90 degree here, 90 degree here. It makes an angle 0 degree here. Here somewhat different angle like this. So like this, neither vertical nor horizontal. Inclination is different at different places. What about declination? Will it be different at different places? Yes. You may be thinking that this angle between geographic and magnetic meridians are same everywhere because it's a fixed plane. No. They make different angles at different places. Declination varies from place to place. How? This is Earth, right? I'll take the Earth once again. This is Earth. Now I will show this pink belt. This is geographic meridian, correct? Now where is magnetic meridian? I think I can better show it using something else. So let me try to dance and I will show it. Then I will show the animation, right? Not now. I will show it. I will show the animation later. Now you see. Say this is okay. I think this is a better choice. One is this one. This is Earth's magnet. Say this is Earth's magnet. I have to think of now. Okay, this is Earth's magnet. Earth behaves like a magnet. Yeah, it is here, right? Actually, Earth doesn't have any magnet. It behaves like a magnet, as if some magnet is kept inside, but Earth itself is a magnet. Okay, the Earth's magnet is like this. And this is the Earth's magnet for the people who are looking from there in your position. Earth is like this, a globe, right? Earth's magnet is like this. Now, say Earth's north pole is here, south pole is here. Earth is a globe like this. You can see it here, right? Earth is a globe like this. And where is the geographic meridian? If you want to have geographic meridian, you have to cut the Earth from here to here like this, taking a knife, because Earth's north pole is here, south pole is here, so cut the Earth like this. That is geographic meridian. What about magnetic meridian? Cut the Earth with that magnet as the axis, so like this. They make an angle theta, that is delta, correct? See, this is the plane for you, because you are observing from there. Suppose you are sitting somewhere here. How does this magnet look like? Just imagine. Earth is like this, and you are living on this surface of the Earth, because you are there. If you are living in this end, what is your condition now? When you are looking at the magnet looks like this. Now for magnetic meridian, you sitting there will cut the Earth like this. That is the magnetic meridian. A person living here on the globe will cut the Earth like this, right? To get the magnetic meridian. Where is the north and south poles of the Earth? Geographic north and south poles of the Earth for a person here. Geographic north is here, south is here. How he will or she will cut the Earth for geographic meridian? Like this way only. What is the angle of declination now? Hope you have followed, right? I feel laughing because this is a very difficult thing to make you to understand. But still, it is a very, very interesting one. I will show required animations and I will try to convince you. Right? This is Earth's magnet which is tilted. For you, magnetic meridian is this one. What is the geographic meridian? This one. Because here is the north pole and here is the south pole. That is for you. For a person living here in this globe here, he says Earth's magnetic field is this one. So he cuts the Earth's magnetic meridian like this. What is geographic meridian for him? North pole, south pole, like this. Don't they lie in the same plane? Yes, they lie in the same plane, and for him declination is 0. Correct? And you just imagine a person who is standing or living somewhere here in the globe here. What is the magnetic meridian? This one. Right? Because he can see the magnet like this. So this is the magnetic meridian. Which is the geographic meridian? This one. Angle changes. Geographic meridian and magnetic meridian, their positions, the angle at which they are inclined keeps on changing when you are living in the different positions on the Earth's surface. Because you just, I will take a small magnet and I will show it. So I will take 2 chalk pieces that may be also, say this is the north and south poles of the Earth. Vertical, right? I'll put this green line. Not, oh, this chalk piece has gone. Shall I take some other chalk piece now, color? Okay, don't have, yes. This is the north and south poles of the Earth, green. What about the Earth's magnetic field? Like this, right? This is the angle of declination. This is for you, remember. So this is vertical and this is Earth's magnetic field is making like this. This is the angle of declination. That is for you. What about for this person? For this person, this is the geographic meridian. Or if you come here, this is the geographic meridian. What is magnetic meridian? This one, same. Both lie in the same plane, because of course I can do one thing. If this is for you, for this person it is different, right? I will turn the Earth like this. Now you see, now you are in this position. So I will turn the person, or I will turn the Earth like this. So this is white chalk is magnet and green chalk is geographic meridian. And now they make an angle for you, right? I will turn the Earth like this. Can you see now? When I turn the Earth and bring it here, now where is the magnetic meridian and geographic meridian? See, it is like this, correct? The magnet looks like this for you. Cut it. If you want to get magnetic meridian, cut it like this. When you cut it like this, you get magnetic meridian. What is geographic meridian? Same, correct? It will be the same. Hope a little bit of understanding will be seen here, right? So if I turn it, you can see this angle. If I turn it like this, you don't see that angle at all. So you cut the Earth like this for magnetic meridian as well as geographic meridian, because magnet is seen like this. So you cut it for magnetic, cut it for geographic. You will see the same angle. So geographic meridian and magnetic meridians they make different angles. So angle of declination goes on changing. So that is one thing about it. So how many terms you have got in this class, you see? Geographic meridian, magnetic meridian, and inclination, angle made by the magnetic needle free to rotate in the vertical plane with the surface of the earth. Angle made by the needle which is free to rotate in the vertical plane with the surface of the inclination. Declination, angle between the geographic and magnetic meridian. And so now we will come back to the important definitions now. Okay. Okay. Now that means if you have Earth's surface like this, suppose the Earth's magnetic field is like this, going inside. It may be going inside and going outside depending on the position, whether you are in the upper globe or the lower globe. So it is going down like this. Now, if this is the Earth's magnetic field, our all experiments are always done parallel to the Earth's surface, correct? We do all the experiments very parallel to the Earth's surface. You keep the magnetic compass like this way on the table. You don't keep all these things in the wall and climb the wall and do the experiment. You always do the experiments on the surface of a table. So everything is parallel to that. So if at all some magnetic field is affecting this needle, means it is the magnetic needle which is parallel to that. We said in the beginning itself, a needle which is turning parallel to the surface of the earth like this stands in the north-south. If it is standing in the north-south, who has made it to stand in the north-south direction? It is the Earth's magnetic field. Which Earth's magnetic field? Full? No, only a component, isn't it? So a needle which is free to rotate like this, right? Which is free to rotate like this has stood like this, correct? Why? Because one component of this Earth's magnetic field has made to stand like this. Because this needle has no freedom to turn like this. That means which magnetic field has made to turn like this? So I will draw one component of this like this, vertical component, and I call it as Z component of Earth's magnetic field, and this is X component of Earth's magnetic field, horizontal component, and I call it as HE. HE means horizontal component of Earth's magnetic field. So any Earth's magnetic field B can be split into two components, a horizontal component and a vertical component. Now tell me, what is this? Is it not the angle of inclination? Because we know angle of inclination is the angle made by the needle which is standing, which is free to rotate in a vertical plane, making an angle with the surface of the earth. Is it not the angle of inclination? Is it not the opposite angle, vertically opposite angle, theta? That means this is theta. Now can you define inclination angle in another way? Angle of inclination is the angle between the horizontal component of Earth's magnetic field and the full Earth's magnetic field. Isn't it? Very simple definition. Angle made by the actual Earth's magnetic field with the horizontal component. That is this one. Now if BE is the full Earth's magnetic field, what is ZE? I'll call it as ZE only. ZE is equal to BE sine theta. Vertical component, we don't have theta here. Here we have theta, that is BE cos theta. For all the experiments that you do on the surface of the earth, usually in parallel to the surface of the earth, it is the horizontal component which affects the instrument. Here, it is a horizontal component. This component doesn't affect at all. The needle compass, if the compass needle is turning like this, for this compass needle, if at all there is a magnetic field which is making it to stand like this way, means it is that component of Earth's magnetic field in this direction. This component cannot do anything for the needle which is turning like this. Hope you have followed. This component of Earth's magnetic field can do nothing for the needle which is turning like this, because this needle can't turn like this. It is fixed with a vertical axis, so it can turn only like this. It can turn, it can turn only like this. It cannot turn like this. So then can I say that a freely suspended magnet stands in north-south direction. That is the horizontal component of Earth's magnetic field. It keeps itself parallel to the direction of horizontal component, that is B cos theta. not in the terms of b sine theta. Whereas a needle which is made to turn like this, it comes to this direction because it is affected by both. It is affected by both. Okay, so Earth's magnetic field can be split into two components, horizontal component and vertical component. Horizontal component is b cos theta, vertical component is b sine theta, where theta is the angle of inclination. You know, this is angle of inclination. Okay, now again coming back to the Earth. Yeah, here this is geographic north, geographic south. This is the Earth's magnetic field starting from here and here. Of course, you forget about geographic north and south. Okay, I will tilt the Earth and I will write the diagram as it is. Suppose this is Earth and this is the magnetic field, and like this. Now come back to the original conditions. What is the inclination here? Theta is 0. 90. What is the inclination here? 90. What is the inclination here? Parallel to the Earth. Theta is equal to 0. Because here a dip needle will stand parallel to the Earth like this. So inclination is 0. Now here the dip needle will stand vertical, right? Like this. Like this. Here the dip needle will stand vertical like this. Inclination is 0 at the equator, 90 degree at the poles. Now my question is, what is the horizontal component of Earth's magnetic field at the poles? What is the horizontal component of Earth's magnetic field at the poles? Remember, at the poles, the whole magnetic field is vertical, right? The magnetic field itself is vertical. What is its horizontal component? 0. Because b cos theta is the horizontal component. Theta is 90. What is b cos theta? b cos 90. There is no horizontal component along or HE, okay, HE at the poles. At the poles, the full Earth's magnetic field itself is vertical. Horizontal component is 0. What about here also? The same thing. Full Earth's magnetic field is vertical. Horizontal component is 0. What about at the equator? At the equator, the full Earth's magnetic field is horizontal, right? Vertical component is 0. So ZE is 0. Earth's magnetic field along the Z direction is 0. Vertical component. So you have so many things to define now, right? One is, so we call all these things as magnetic elements. Suppose you want to find out what is the strength of Earth's magnetic field at a point on the surface of the Earth, on the globe. If I want to find out what is the magnetic field here, where is India? At here, near Delhi, what I have to do? You have to know three things mainly. They are called magnetic elements. The quantities which are required to find out the strength of the magnetic field at any point, they are called magnetic element. There are three magnetic elements: the declination, the inclination, and the horizontal component of Earth's magnetic field. These three things are very much needed. So what is declination? Angle between geographic meridian and magnetic meridian. What is inclination? Angle between the Earth's magnetic field and the horizontal component. Very easy. Angle between the Earth's magnetic field and the horizontal angle between the Earth's magnetic field and its horizontal component. That is called inclination. Okay. What is meant by horizontal component of Earth's magnetic field? Component of the Earth's magnetic field along horizontal direction, parallel to the surface of the Earth. That is called horizontal component of Earth's magnetic field. What is the value of horizontal component at the poles? At the poles, whole magnetic field is vertical. Horizontal component is 0. What is the value of horizontal component at the equator? Full Earth's magnetic field. It itself is full parallel, right? What is the vertical component at the equator? 0. What is the vertical component at the poles? Full Earth's magnetic field. Okay, then what else? What is magnetic meridian? Magnetic meridian is a plane vertical to the Earth but passing through the axis of a freely suspended magnet. What is another geographic meridian? Geographic meridian is a plane passing through the geographic north and south poles of the Earth. Will they make the same angle everywhere? No. What is declination? Angle between the geographic and magnetic meridian. That depends on how do you see the Earth, right? From which point you see the Earth, because they make different angles at the different places. All these definitions are very important, and of course you must understand this. This is like somewhat general knowledge. and it is needed for the examination point of view also. Hope you have enjoyed this class, because I was doing so many things there, and we will have some animations for this. I will try to get them and put it in a PPT, and I will show it to you so that it will be very clear. If it is clear, then this chapter will be very easy. So we will come up with few more things in the later classes. Till then, keep on studying, don't waste the time, because they are very, very important chapters as far as the theory exam is concerned, and also the entrance exam. Hope you will read well. Thank you for watching the class. Thank you. We will meet in the next class.